Kind of wild. We are at the end of derivative rules. I think I'm going to make another video on logarithmic differentiation, which kind of involves logarithms, but that's not part of Calculus AB. So we get through this and we are kind of ready. That's pretty exciting. So the last thing is the derivative of exponential and logarithmic functions. By now, you know the derivative of e to the x, so we're going to transform that into kind of the way we did with inverse trigonometric functions. We'll find the derivative of natural log of x. Then we can go back and forth. We'll be able to find the derivative of logarithmic functions of all bases, not just base e, and the derivative of exponential functions of all bases, not just base e. And that's, you know, if you have implicit differentiation, we're good to go. So in my class, I think the best way, somebody taught me this a long time ago. I think back when I taught AB and there was another BC teacher, Mr. Harrison. Instead of saying the derivative of e to the x is e to the x, because we use that one all the time, we just say the derivative of e to the x is e to the x natural log of e. And then you won't forget another rule that we don't use quite as often. So in order to do this stuff, I know my kids are going to need a little bit of a refresher on logarithms. And if you can just remember in one word that a logarithm is an exponent, you're good to go. So you read this as log base 4 of 64. Log base 4 of 64 is 3. Because 3 is the exponent, you put on the base 4 to get 64, right? We say base here, log base 4 of 64. And we're looking for an exponent. What exponent are we looking for? The exponent we put on 4 to get that 64, and turns out that's a 3. Okay, so let's do a few more of these. You can kind of just follow along. Log base 2 of 8 is 3, because 3 is the exponent. You put on the base 2 to get 8. Log base 4 of 16 is 2, because 2 is the exponent. You put on the base 4 to get 16. I don't like the color palette. Red doesn't match, and for some reason, PowerPoint really wants me to have red to begin with. Okay, log base 3 of 81 is 4. 4 is the exponent. We put on the base 3 to get 81. You should be able to say these things. The more you, instead of just yelling out 3 or 2 or 4, the more that you can use these vocabulary words, the more you're actually going to understand logarithms and other things. If you really want to understand logarithms, buy a slide rule. Log base 8 of 4. That's a little hard because 8 to the first power is 8. 8 to the 0 power is 1. So this is somewhere in between. So maybe we can use change of base. Let's see. What do 8 and 4 have in common? They have in common 2, or at least that's kind of like the way my brain goes. So that's like log base 2 cubed of 2 squared. And how do we turn 2 cubed into 2? We take the cube root, so that would be an exponent of 1/3, and then we square it. And you can check that in your calculator, that 8 to the 2/3 power is 4. And of course it is, because you're doing the cube root of 8, 2, and then squaring that to get 4. There's another one underneath, so that's going to pop up. Sorry. So log base 8 of 16, there we go. Well, 8 to the first is 1, 8 squared is 64. I guess we need to change this to something else. And you could, I guess, change them both into 4s. 16 is 4 squared, but it's probably easiest to do the cube root of 8, just like we did, and then we're going to raise that 2 to the 4th power. 4/3 is the exponent we put on 8 to get 16. All right, a few tricks here. Log base 9 of 81. Well, log 1 over 81. Log base 9 of 81 is 2, and we have the reciprocal there. Don't forget, a logarithm is an exponent, and the exponent we put on 9 to get the reciprocal is not 2, but -2. So log base e of e is a ridiculous question. Obviously 1 is the exponent we put on e to get e, but people get confused when we write natural log of e. Natural log of e just means log base e of e, so that is 1. And, okay, natural log of 1 over e. What exponent do we put on e to get 1 over e? -1. Hopefully that's a nice refresher on logarithms. If that wasn't good enough, you probably need to go back and do more logarithms. So that's kind of all you need to know how to find the derivative of natural log of x. We don't know how to find the derivative of a logarithm yet, so let's get rid of the logarithm. And natural log asks the question, what exponent do you put on the base e? So the inverse of that is e to some exponent. So just like natural log of e is 1, e to the power natural log, or another way to say that, how about this? Let's write it this way. Log base e of e to the x would be x. Because this asks the question, what do we put as an exponent on e to get e to the x? And the answer is, of course, well, x or whatever this exponent is. And so e to the power natural log of x, well, those are the exact same inverse functions, just in reverse order. So we get e to the y is equal to x. And then we notice, okay, I can do the derivative of e to a power, and I can do implicit differentiation, and the derivative of x is 1. So the derivative of e to the y is e to the y, chain rule dy dx, and the derivative of x is 1. So we want dy dx, the derivative of this original y, divide by e to the y. Dy dx is 1 over e to the y. That doesn't look right for the derivative of natural log of x. So we just need to find out how we can get rid of that y. And you might be thinking, put natural log of x in for y, and that will totally work. But the easier way is we have right here, e to the y is equal to x. So the derivative of natural log of x is 1 over x, or the derivative of natural log is 1 over the input. Do I have this ready to go? So graphical confirmation, I don't know. Apparently not. Let's click on this. And so I made a Desmos thing. Hopefully I will remember to attach that if you want to play with this. So I have natural log, and Desmos will give us, can we zoom in? There we go. Desmos will give us a derivative. So I just have this movable point C. And here at 2, right, that's definitely 2 in natural log. That's our point 2, and I'll just have to trust that. And we can see the slope of the natural log graph at 2 is 1/2. Let's move this to 3, just some easy numbers. The slope of the natural log graph at 3 is 1/3. I guess you're going on faith here, who knows. The slope of the natural log graph at 4 is 1/4. Hopefully that's enough confirmation that the derivative at a point, the slope of natural log at any point, is 1 over that x value. Okay, so let's put that into action with a few examples. We're going to find the derivative of natural log of 3x with respect to x. And so obviously this is a chain rule. The derivative of natural log of something is 1 over that something. That something is 3x, so chain rule times 3. And we will simplify. 3 divided by 3 is 1, so we actually just get 1 over x, which always bothers me. I feel like a 3 should show up. All right, so another chain rule situation, the derivative of natural log of x squared. We're going to do the derivative of natural log is 1 over the input. That input is 2x, which has a, oh, sorry, my brain is stuck. That input is x squared, which has a rate of change of 2x. And so, of course, one of the x's divides out, and we get the derivative of natural log of x squared is 2 over x. How are we going to find the derivative of x natural log of x? Product rule. The derivative of a product of two functions is the first function, x, times the derivative of the second, and I guess I'm looking at it. X is one function, natural log of x is the other, so the derivative of natural log of x is 1 over x. My cat's going nuts. Plus the second function, natural log of x, times the derivative of x, 1. So x divided by x is 1, and we get the derivative of x natural log of x is 1 plus natural log of x. That seems unsatisfying. Just a couple more here. So the derivative of x divided by natural log of x, we're of course using the quotient rule. Denominator, natural log of x, times the derivative of the numerator, derivative of x is 1, minus the numerator x, times the derivative of the denominator, derivative of natural log of x is 1 over x, all over the denominator squared. And really the only simplification we can do is x divided by x. So the derivative of x over natural log of x is natural log of x minus 1 over natural log squared. All right, so now that we know the derivative of natural log, we can find the derivative of any other exponential function. So we'll prove a rule here, but let's try to figure this out. So just like we did with inverse sine, inverse cosine, with natural log, we don't know the derivative of 2 to the x, so we'll do something that allows us to rearrange. And that's a logarithm. The reason we choose natural log instead of log base 2 is we're trying to do a derivative, and at this point we don't know the derivative of any log except natural log. And we probably would anyways, because natural log is the easiest derivative. Okay, so logarithms allow us to move exponents, so this exponent on 2 is going to become the coefficient out front. And also key, this natural log of 2 is a constant. So when we take the derivative of that right-hand side, that's the same as taking the derivative of like 5x. The derivative of 5x is 5. The derivative of 4x is 4. And so the derivative of x natural log of 2 is simply 1 times natural log of 2. Okay, so on the left-hand side, derivative of natural log of something is 1 over that something. That something is y, which has a rate of change dy dx. So we're going to multiply both sides by y, and way up top, y is equal to 2 to the power x. So on the left-hand side, we'll multiply by y, and on the right-hand side, we'll multiply by what y is equal to 2 to the power x. And so the y divided by y is 1, and over here, it looks better to have the 2 over x out front. So the derivative of 2 to the power x is 2 to the power x, natural log of 2. Which is why I'm going to be saying in my class the derivative of e to the x is e to the x natural log of e. That's just, I don't know, people always forget about this natural log of the base over here. Okay, let's try that again with a different base. Write it down, y equals 3 to the power x. Maybe you know what the derivative is going to be, but let's try to do all of the work in case we need to do that sometime in the future with something more complicated. Take natural log of both sides. Natural log of y is natural log of 3 to the power x. Move that x out front of the natural log of 3. And remember, natural log of 3 is a constant. So the derivative of a constant, natural log of 3 times x, is that constant times 1. So the derivative of natural log of y is 1 over y dy dx. And we'll multiply both sides by y, literally y on the left, and what y is equal to 3 to the power x on the right-hand side. And the derivative of 3 to the power x is 3 to the power x natural log of 3. Okay, see if you can get this one done a little more quickly. The derivative of 4 to the power x, hopefully you know, is going to be 4 to the power x times the natural log of 4. We'll take natural log of both sides. So natural log of y is equal to natural log of 4 to the power x. Move that x in front of the natural log of 4. Natural log of y is x natural log of 4. Natural log of 4 is a constant, so on the right-hand side, we get a derivative of 1 natural log of 4. The derivative of natural log of y is 1 over y dy dx. Multiply both sides by y, and we indeed get the derivative of 4 to the power x is 4 to the power x natural log of 4. So pretty easy. If we know derivative of 2 to the x, 3 to the x, 4 to the power x, well, any allowable base a, so I suppose we could say a could be 1, but really any positive base, we would just take natural log of both sides, move that x to be a coefficient in front of the natural log, And natural log of some constant is going to be another constant. So same thing here. Derivative of x times natural log of a is natural log of a. Multiply both sides by y. And the derivative of a to the power x is a to the power x natural log of a. Cool. Only one more derivative rule to go. And that's logarithms with a base other than e. So one way to go is to just use change of base formula. So log base 2 is the same as natural log of x divided by natural log of 2. And you can think of this I suppose it's my fault for switching back and forth between light and dark. So this is the same as 1 over natural log of 2 times the natural log of x. So we can think of that natural log of 2 as multiplying by a constant instead of dividing by a constant. And the derivative of natural log of x is 1 over x, and that natural log of 2 just stays there. The other way to go is to raise both sides as exponents on 2, exponentiate both sides. So 2 to the power y is going to be equal to x, and then we can use the rule we just had. So the derivative of x on the right-hand side is 1. The derivative of 2 to the y is 2 to the y, natural log of 2, chain rule dy dx. All right, and then we divide both sides by 2 to the y natural log of 2. Well, what happened there? Let's think about that for a moment. Well, so over here I'm going to divide by 2 to the y and natural log of 2, pretty obviously. And over here I'm going to divide by natural log of 2, but instead of 2 to the y, I'll divide by what 2 to the y is equal to, x. Maybe I should have done that in 2 steps. Oh well. So kind of the same thing. We can prove that last derivative rule 2 ways. We can just rewrite log base a of x as natural log of x over natural log of a. And the derivative of that natural log of x is 1 over x. Natural log of a is a constant, so we can just kind of ignore it when we do our derivative, constant multiplier. The other way is to raise both sides as exponents on a, so a to the y is equal to x. The derivative of a to the y is a to the y, natural log of a, dy dx. Derivative of x is 1. And remember, a to the y right here counts as x, so when we divide a to the y natural log of a on both sides, we might as well make the swap a to the y is equal to x. So that's the last derivative rule. The derivative of log base something of x is 1 over x, just like natural log's derivative. Natural log of that base a. So the way I'm going to say it, the derivative of e to a power is e to that power, natural log of e, and then if you need to, chain rule times the derivative of that power. I won't typically write the natural log of e, I will just say it, and the reason I'm going to be saying the natural log of e there is that comes up, e to the power x, e to the power whatever, a whole lot more than 2 to the x, 3 to the x, which means that's just opportunity for practicing. The derivative of a constant to a power, or 2 to the power, 3 to the power, is that base to that power, natural log of the base. The derivative of natural log is 1 over x, or kind of like we do with e to the x, maybe 1 over x natural log of e, also in that denominator. The derivative of log base something is 1 over x, natural log of the base. And of course you could do chain rule here, but hopefully chain rule is no problem. Let's do a few examples to close this out. So the derivative of natural log of 2x cubed, well, the derivative of natural log of something is 1 over that something. That something is 2x cubed, which has a rate of change of 6x squared. And then 6 divided by 2 is going to be 3. X squared over x cubed gives us an x in the denominator. You know, another way to do that would be to just move this 3 to be out front, coefficient. Heck, maybe we should do that. Y is equal to, oh no, we can't do that, right? Because that 3 is an exponent on the x, not on the 2, and I don't feel like doing that algebra. Okay. So y is equal to the natural log of 2e cubed. What's the derivative of natural log? Doesn't matter, because natural log of 2e cubed is going to be 0. I like to try to make sure my kids are paying attention. If we're doing this chronologically, last night they had a problem set where like a third of them had a derivative of 0, trying to get them to pay attention to constants for some reason. And I know why. We don't see e as a number the way we see pi as a number or 6 as a number. All right, so we do indeed have a variable here, the derivative of natural log of 2x cubed. So we'll take the derivative of that outermost natural log first, which has a derivative of 1 over whatever the input is. That input is natural log of something else, which has a rate of change of 1 over that something else. That something else is 2x cubed, which has a rate of change of 6x squared. So I can't really simplify this natural log part, but over here the 6x squared over 2x cubed simplifies to be 3 over x. So 3x times 2 to the power 5x, that's going to be the derivative of a product of two functions, which is the first function, 3x, times the derivative of the second. And I know that's going to take me a moment, so I'll leave a blank there and fill in while I copy down the second function, 2 to the 5x, times the derivative of the first function. The derivative of 3x is 3. Okay, so now we can just focus on the derivative of 2 to the power 5x. And this is the one people forget. So the derivative of e to the x is e to the x. The derivative of 2 to a power is 2 to that same power. Natural log of the base. And don't forget chain rule on that 5x. And apparently we can simplify that a little bit. Both terms have a 3. Right? This first big one, right? All that is multiplication. So we'll just pull out the common factors. And that's a 3 and a 2 to the power 5x. So we're left with, x. And then just to remind people, you can move that coefficient 5 to be the exponent on 2. 2 to the 5th is 32. All right. So again, a product rule, the derivative of x times e to the x squared. We can't simplify anything first. There's no natural log here with the e. And the derivative of a product of two functions is the first function x times the derivative of the second function plus the second function e to the x squared times the derivative of the first. And let's go back. The derivative of e to a power is e to that same power. That power is x squared, so chain rule times 2x. Can we simplify? Can we rewrite? Yeah, we can factor out an e to the x squared, and we'd be left with 2x squared plus 1. You're welcome to try this out. It's mostly me being ridiculous in class because, let's see, what do we have here? Well, the easiest thing to do structure-wise is we have two terms added together, so we can do those individually. The right-hand side really won't be a problem. Natural log of secant, although that's a little involved. But the left-hand side, you have to deal with e to a power first. And then inside of that power is a product of two functions. And one of those functions is a quotient. And inside that quotient, let's see, is a chain rule on this sign. And if you want to do that on your own and check, here's what I wrote out.